In 1886, London started building a bridge where it seemed almost impossible to build one. This part of the Thames was packed with tall cargo ships. A normal bridge would block them. Raising the road above their masts would mean building massive ramps straight through East London. More than 50 designs were presented, but no one was good enough to satisfactorily enough. Then engineers suggested something that sounded insane at the time. They would place two huge towers in the middle of the river and make the road between them move whenever a ship arrived. Those moving road sections would weigh more than 2,400 tons together. Remember, it was 1886. There was no huge machinery. Well, first of all, we need to see why London needed such a strange bridge at all. By the 1870s, factories, docks, and crowded neighborhoods had spread along both sides of the Thames in East London. But London Bridge remained the nearest major road crossing. People and horse-drawn carts had to travel toward it, adding even more traffic to the surrounding streets. The river below was just as busy. Tall-masted cargo ships moved through the Pool of London to reach wharves farther upstream. Building close to the water would seal off those docks. Engineers considered raising the road above the ships, but that required long, steep ramps cutting through existing streets and buildings, and that wasn't feasible at the time. London needed a road close to the river that could somehow move out of a ship's way. Now officials had to find a design capable of doing it. London officially began that search on February 10, 1876, when the city formed a special committee to study a bridge or tunnel. More than 50 designs arrived. Some engineers proposed tunnels, while others drew complicated bridges with sections that rolled or moved. By 1879, the committee had dropped the entire competition without choosing a winner. City architect Horace Jones continued developing his idea and later teamed up with civil engineer John Wolfe Barry. On October 28, 1884, they presented a new plan. Suspension sections would carry the road toward two towers. Between them, the roadway could open for ships, and walkways high above would keep pedestrians moving. The Tower Bridge Act became law on August 14, 1885. Workers broke ground the following April. But before they could build the towers, 6 divers had to disappear beneath the Thames. The divers wore heavy canvas suits with copper helmets. Air hoses connected them to hand-operated pumps on the surface. A man named Friend Samuel Penny led the 6-person team. Ships still needed to reach the wharves, so workers couldn't dam the entire river. Cranes lowered huge open iron boxes into one section of the Thames at a time. Engineers called them caissons. Penny's team surveyed and leveled the muddy riverbed before climbing inside the boxes. They removed gravel and clay from beneath the edges. Every load they dug out allowed the caisson to sink farther under its own weight. Some foundation sections reached almost 8 meters beneath the riverbed. Crews then pumped out the water, poured concrete into the foundations, and built upward with brick and granite. Cargo ships continued passing through the remaining channel as 2 enormous piers slowly rose from the Thames. Those piers looked solid from the outside. Inside, engineers left enough empty space to hide something enormous. And somehow, they had to lift them without a single electric motor while keeping the river open during construction. So how did they pull this off? And why should Tower Bridge have been impossible in 1894? Inside each pier, workers built a huge empty room called a bascule chamber. Each chamber measures roughly 21 meters wide and 59 meters long. From bottom to top, it rises 27 meters, about the height of a 9-story building. Brick walls around 3 meters thick hold back the river, while granite protects the outer surface. These chambers gave the bridges enormous counterweights somewhere to move. Whenever the road lifted, the weights behind it would swing down through these spaces. The piers also carried the road's pivot shafts and operating machinery, with the towers rising directly above. So, before Tower Bridge could move at all, workers had to build 2 underground machine rooms inside the Thames. Once those piers were ready, construction finally moved above the water. And at this stage, Tower Bridge looked nothing like the stone castle we see today. Sir William Arrol and Company manufactured its structural parts in Glasgow. Crews then assembled more than 11,000 tons of steel into the bridge's hidden skeleton. 4 octagonal steel columns rose inside each central tower. Huge plate girders tied them together, while diagonal braces stopped the structure from twisting under heavy loads and strong wind. Steam cranes lifted each new steel section into place. Once workers completed one level, they raised the cranes onto it and continued higher. Riveting gangs followed behind. One worker heated each rivet until it glowed. Another threw it upward to a catcher waiting with a bucket. The team pushed it through the steel and hammered the end flat. As the rivet cooled, it shrank and pulled the steel plates tightly together. Workers installed millions of them. Around 432 people worked on the site each day, and more than 2,000 contributed during the 8-year build. By the time the steel towers reached their full height, crews still had to connect them above an active shipping route. They couldn't simply fill the river with scaffolding. So crews built the walkways from the towers themselves. They fixed the first steel sections above each tower, then moved cranes onto the finished work. From there, the cranes reached forward and added the next sections. Both sides slowly extended over the river until workers joined them in the middle. The finished walkways stretch about 61 meters between the towers and sit 42 meters above the Thames. They also perform a structural job. Huge steel ties running along them connect the suspension systems that carry the roads on either side of the bridge. This keeps those side spans balanced against each other. Far below, ships continued moving past the workers. Every tool and hot rivet had to stay out of the water and away from the vessels underneath. Now the towers connected at the top. At road level, a 66-meter gap still separated them. Engineers filled that gap with 2 moving road sections called bascules. The name comes from the French word for seesaw. Building them flat would block the shipping channel, so crews used a much stranger method. They first assembled the rear ends and short sections near the pivots. Workers then lowered the incomplete steel girders into the chambers, turned them upright, and installed the permanent pivot shafts. From there, crews added the remaining steel while each bascule stood almost vertically. Each finished road section weighed more than 1,200 tons. Behind its pivot, workers packed roughly 422 tons of counterweight into the shorter end. That concentrated weight almost perfectly balanced the much longer road section stretching over the river. The river end remained only around 7 to 5 tons heavier, so the machinery didn't need to lift the entire 1,200-ton bascule. It only needed to overcome that small difference, along with friction and wind. As the road moved upward, its counterweight swung down into the chamber beneath the tower. The force that started this movement came from an engine room beside the southern approach. Workers shoveled coal into large boilers, which heated water and produced steam. That steam powered 2 pumping engines. Their pistons didn't move the bridge directly. They forced water into 6 huge hydraulic accumulators at roughly 750 pounds per square inch. Heavy rams sat on top of those accumulators. As pressurized water entered, it pushed the rams upward and stored energy for the next bridge lift. You can think of them as giant Victorian batteries. When a ship arrived, an operator opened the valves. The heavy rams pushed the stored water through pipes toward drive engines inside the piers. Their pistons turned large cogs. Those cogs grabbed curved-toothed racks attached to the bascules and began rotating the roads upward. The hydraulic system also pulled back the locking bolts joining the 2 road sections in the middle. Engineers installed backup machinery on both piers so one mechanical failure wouldn't trap the bridge in place. By April 1894, every part of this steam-powered system was ready for its first full test. In April, Sir William Armstrong's engineers raised and lowered the completed bascules for the first time. By then, Tower Bridge had finally gained the appearance we recognize today. Stoneworkers had placed the last external granite block on January 31, 1894. Cornish granite and Portland stone now covered the steel towers, making the machinery inside look like part of a medieval castle beside the Tower of London. Then came the weight test. On June 21st, crews packed the road with steamrollers, traction engines, and heavily loaded trolleys. The bridge held. 9 days later, at noon on June 30th, 1894, the Prince of Wales officially opened Tower Bridge beside Princess Alexandra. Workers spent 8 years building the bridge and used around 31 million bricks. The steam-powered system kept lifting Tower Bridge for more than 80 years. Engineers began replacing it in 1974 and completed the change in 1976. Today, electric pumps pressurize oil to power the bridge, while much of its original lifting mechanism continues doing the job Victorian engineers designed it to do. Now, if huge projects and insane engineering are your thing, make sure to hit subscribe to the channel. And while you're here, check out our previous video on the $20 billion tunnel that flooded before it opened. Water was pouring into the Boston Big Dig at up to 50,000 gallons a minute, and the engineers responded by doing something that sounded completely backwards. So go ahead and check it out.